Hello, so here is chapter 2 of the Basic Practice of Statistics, 9th edition. So in this chapter, we're going to cover two different measures of center, the mean and the median. And then we're going to talk about how we compare them, and why we compare them. And then we're going to talk about measuring variability with the quartiles and the 5-number summary. We can also learn about a new plot, that's the box plot, and also outliers and measuring variability using the standard deviation, and when should we use, which measure of center should we use and which variability should we use? Should we use the 5-number summary or should we use the mean and the standard deviation? And we will take a look at these right now. So everyone should know how to calculate the mean. It's also called the average. So if you have, let's say, 4 grades, the first thing you like to do is add those grades up and divide by 4. If you have 4, so you add them up and you divide by the total and you get your average grade. And so we do this using this notation. It's a standard notation. It's called X bar. And it looks just like that, X with a bar on it. And what it is in notation is X1 plus X2 plus and so on till you get to Xn, where N is the total. The N is the total number of items that you're adding up. So if it's grades and you have, say, 4 grades, X1 could be maybe your history grade, X2 could maybe be your math grade, X3 could be maybe your stats grade, and you get the idea. And then you divide by N, which is the total number of grades. In compact notation, X bar is essentially just 1 over N, 1 divided by N, and that sigma comes from the Greek alphabet, sigma, and it's a little counter. It means to add. And we have X subscript I. For I equals 1, that's a 1 there, to N. And so that's just a shortcut to saying we want to add these up and divide by N. So X bar, which is our mean and our average, it all means the same thing. And X bar is not a resistant measure. So what does that mean? It means that if I were to, you'll get a sense of what this means more with the example that we're going to do, but it basically means that it's very influenced by more data. So if we introduce new data, or if we have high values in the data set or low values in the data set, it doesn't even need to be new data. It's just high extreme values or low can change the mean, whereas the median is a position. It's the center of the data. So it's, if you were to cut the data in half, then you can find the median. The median means the middle, and we denote it with a capital M. So the median is a resistant measure, meaning if you change anything, if you change the values just slightly or add a value, which we'll see here in the next example, then you will see the median may change a little or it may not change at all. Okay, so you can use this little formula, the bottom, n plus 1 divided by 2. Observations will give you the position or location of the median. And N, to remind you, N is the total number of observations in our data set. Okay, here is the example that was used. We have 4 grades, 64, 75, 73, and 83. Calculate the average. We add them up, 64 plus 75 plus 73 plus 83, and we get 295, and we want to divide by 4. That's the total, and we get an average. X bar equals 73.75. To find the median, which is denoted with a capital M, we need to remember, and this is important, we need to order the statistics from smallest to largest. So we need to put the 64 first, then the 73, then the 75 and 83. It may not matter in this case. In fact, it doesn't. But It could in other data sets. So you need to make sure that they are from smallest to largest. And then you cut the data in half, which would be 2 on the left and 2 on the right. So we have an even number of data points here, and we simply add 73 plus 75 and divide it by 2, and we get 74. So our median here is 74. So on example 2, this is example 1, this is example 2. What if we went, hey, we forgot about that 92. We need to get a 92 in there. That's another grade. So we calculate X bar again. You need to recalculate it because it needs to be added into the formula and divide by 5 this time. So we add them all up, divide by 5, and we get 77.4 is the average. And it changed quite a bit. If you look, it went from 73.75 to 77.4. So it really increased the average of these grades just by having that 92 in there. The median, however, we order them from smallest to largest, 64, 6, 73, 75, 83, 92. Because we have an odd number of observations, we then literally take the value in the data set that's in the middle, and that is 75. Okay, and that is the median, 75. So just to recap about the process of getting those medians is if you have an even number, you slice the data set in half, then you take the average of those points on either side, 73 and 75 in that case, and then take the average of those two. And if you have an odd number of observations, then you will have the median within your data set. It will be right there in the middle. So it's part of the data set. Okay, you don't need to calculate anything. So let's compare 74 without the 92 missing value versus 75 with the missing value. So the median did not really change much, whereas the mean did. Okay, so that's the difference between it is resistant measure, that's the mean, versus it's not resistant, the median. And here we looked at also the North Carolina. So these are the times, these are the commute times in minutes for 15 workers in North Carolina. And it's not ordered from smallest to largest. It is in this little stem plot. See, I told you you would see some stem plots here and there. So it is in order. So we have 5 minutes, and then 8 minutes, then 10 minutes, then 12. It's a nice way to kind of order it. If you want to order your data that way, you can in a stem plot. Again, though, just to remind you, you won't be directly tested on stem plots. But you can see for small data sets, they can be kind of useful if you're trying to figure out what the median is or later on the quartiles. Okay, so with this data set, the calculation is done there in the middle of the slide. 20 plus 35 plus 8 and so forth. Divide by the total n, which is n in this case is 15. We get 25.3 minutes. Versus the middle observation for these 15 data points, if we order them from smallest to largest, we get 20 minutes. Okay, and from those two values, they're different enough for us to say that we probably have a right skewed distribution. So the takeaway here is if the mean is greater than the median by a fair amount, in this case, it's 25.3 minutes versus 20, then we can say that the data set is most likely right skewed. And you can see that here, I drew it with the histogram. It's decreasing to the right, which is the larger the value, the large values. As we go from the top to the bottom, it's getting larger. Okay, so the 25.5 would be about here, 25.3 would be about here, and the 20 would be about there. And so we have right skewed. And so if the distribution is right skewed, then we calculate what is called the 5-number summary. And we did that. We have a minimum value, which is 5. the largest or maximum value is 70. We calculated the median, which is 20. And then what you do to get the quartiles is you take a look, you just basically cut the data in half again. So you cut the data in half to get the median. And then you look at the bottom half and you cut it in half, find its median in the lower part, which is Q1, and you do the same thing for the top part of the data set, and that's Q3. And then you have those 5 numbers. Okay, we'll come back to those in a moment. This is a slide that talks about comparing the mean and the median. So if the mean and median are approximately the same, then we probably have a symmetric distribution. It's probably roughly symmetric, maybe not be exactly, but it will be close. If the distribution is exactly symmetric, though, the mean and the median will be exactly the same value. In a skewed distribution, though, the mean is usually farther out in the tails than the median. So just like we have here, the mean was farther in the tail, so that means we have right skewed. If it was the other way around, we'd have left skewed. And there's the quartile. So this is what we use. We have the min, the max, the median, which is the median can be sometimes Q2, and the quartiles, Q1 and Q3. So let's see what they are about. Right here on the bottom of this slide, it shows what the 5-number summary percentage of the data points there are. So between the minimum and Q1, 25% of the data lies between those two values. Between Q1 and the median, we have another 25% of the values. And then between the median value and the Q3 value, we have another 25% of the data. And finally, between Q3 and the maximum, we have the last 25%. So if you have 25% plus 25% plus 25% plus 25%, you have a total of 100%. So between Q1 and Q3, you have 50% of the central data. So it's 50% of the data. And this is useful because we can plot this and we can compare distributions using the box plot. And it shows how to create the box plot, but I think it's better to just see it. So here are the commute times for 20 travelers in 20 workers in New York. We already did for North Carolina, but this time it's for New York. And we have the min, we found the Q1, the median, the Q3, and the max. You can see how they calculated that. They rewrote the raw, this is the raw data up here. That first row is the raw data. The second one is the ordered data. That says ordered. And from smallest to largest. And from there, you can get your minimum value, 10, maximum, 75. And then from there, you slice the data in half to get your median right here. That's the average of 30 and 35, which is 32.5. And then you do that same thing again. You look at the bottom half and you slice it in half and you go, okay, what's the average between 12 and 15? Right? Because you can see there's 4, 5, 6, 7, 8, 9, 10. And then there's 10 values here and there's 10 values here. And that's how you cut them in half to get the Q1 and also the Q3. 50 plus 50 is going to be divided by 2. That'll give you 50. It's obvious, but that's the process used to find the quartile. Okay, so we have our 5 numbers. We then can plot these into a box plot, the 2 distributions, North Carolina and New York being the top, and immediately we can analyze this and see that the New York workers have a longer commute time than the North Carolina workers, just from the box plots. These are horizontal box plots. They are lying horizontally. They can be vertical if we were to flip the X and Y axis. Sometimes they're shown that way. In this case, it's shown horizontally. And you can see where the minimum corresponds to that first whisker tail right there. Q1 equals 13.5. It's going to be right at the top of the box, which is right about 13.5 will be right at there. And then the middle line of the box, that's the median, which is 32.5, which is going to be about right there. It lines right up on that number line. And Q3 is 50, which is exactly right there. That should be where the top of the box is. And then the whisker there is 75, which corresponds to the center here, 75. And the same thing can be done for North Carolina. You can compare these commute times for all of these workers. And back here, the 5-number summary was calculated for North Carolina on this slide right here. We found the min was 5, the max 70, the median 20, and then Q1 was found to be 12. We did that from the stem plot here. There's the 1, 2. And the Q3 is 35 right there. So it was this 5 right here, 35. And that's how we were able to find them. And then we were able to plot them. Once we plot, that's what the box plots are best for comparing distributions. Just a single plot, like suppose we just had New York, it would be kind of boring just having the one box plot with those values. It's, I guess, a little informative, but it's even more informative if you're comparing distributions. So it's best to compare them when you have more than one box plot. Here we have 2 on the same plot, and the North Carolina had an outlier. If you scroll back, you'll see on that previous slide with the North Carolina data that there was somebody took 70 minutes to get to work. And so that may have been a recording error, or it really could have taken 70 minutes for that worker to get to work. All right, so it's something that we investigate. We always take a little closer look at the way things were recorded. Was it a typo when we do see these outliers, just to be sure. And you can see it corresponds to 70. All right, moving on to the interquartile range, the IQR. Now, if we want the full range of the data set, that's, if we want to know like how spread out are the observations or how close together, we just take the max, the largest value, and subtract the min, the smallest value. So max subtract min, that's the formula. If we want to know the interquartile range, basically the width of the box plot, we just take Q3 and subtract Q1, and it will tell you the width of the box. Using the IQR and multiplying that by 1.5, we can use that little formula to find out whether an outlier is an observation is an outlier, a suspected outlier. So we want to see, do we have an outlier? So an observation is an outlier if it is greater than Q3 plus 1.5 times the IQR, or if it's less than Q1, subtract 1.5 times the IQR. Basically, if it's really, really small below the box or really, really extremely high above the box, then we know. So those are the mathematical formulas. That should say R, IQR. Those are the mathematical formulas that help us determine whether we have an outlier or not. And then we look closer to see, is it a typo or really was it part of the natural phenomena? And so we did that. Here, we calculate right here with the North Carolina, right at the top of the page here, the top of the slide, 1.5 times the IQR plus Q3, and that came out to 69.5. So any value that is greater than 69.5 in the data set, which is right here, 70, is deemed a suspected outlier. We say suspected because it could be a typo that gets corrected. Okay, so for the time being, we'll call it an outlier. And so on this page coming up, right here, they calculate those formulas using the New York data, and they come up with this value here, negative 41.25 and positive 104.75. And you can see there are no values. If you go to the raw data on that slide, you'll see there are no values less than negative 41.25 or greater than 104.75. So there's no travel time shorter than negative 41 point, you can't, right? It's not even possible. So that's not even possible. And there's no commute times greater or longer than 104.75 minutes. So mathematically, it might come out as negative time, but we know that it's just the math. It's not physically possible. So therefore, we conclude that none of the observations in the New York data set would be considered suspected outliers. All right, and it's just talking more about it and where the cutoff is. So you can read that slide and I will go on. These slides are all posted on Brightspace. Moving on to the variance. Now, the variance is whether we want to know how far are the observations from each other, from the mean in particular. So the average distance from the mean for each observation, and then we square them and divide by n-1. And the variance tells us how spread out those observations are or how close together they are. And in compact notation, again, we have our sigma, and we just, this should be a little I. I see a little typo there. I think it should be a little I subscript, and subtract x bar. And then what we do is because it's in squares, we wouldn't want, like, say, kilometers squared. So we would want to take it back to the original units of the data set. So we take the square root, and then when we do that, we don't have the variance anymore. We have the standard deviation. So the variance is s squared, and it's the sample variance to be specific. We're assuming we're taking a sample from the population, and the sample standard deviation is denoted with an S. So the variance, S squared, and the standard deviation, S. And here is showing what it means in a picture. Here we have 5, n equals 5 values, right? 1, 2, 3, 4, 5. And they are scores, they are SAT math scores from a university. And we can see that the average was calculated to be right here in the middle as 548. And so to calculate the variance is we want to know what the deviation is. That's the distance from the mean. So our value, say 490, is an observation. How far is 490 from 548? Well, it's negative 58. And then how far is 650 from the average? Well, it was, if you just subtract it, you get 102. So we calculate all of these averages and we square them and divide by n-1 to get the variance. And the variance is a number that tells us how spread out the data is or how close together it is. And so it is calculated pretty extravagantly. They really decompose how they do it. They do the subtraction for that, and they get these values, and then they square them, and then they add them all up, and then they take the square root, and we get 78.87. Now that's a SAT math score. So in the context of this, it's not really a large variance, I wouldn't really say, from 450 to 650, maybe 200. Well, the variability when you take all the data points into consideration is only 78. So the smaller the variance, the less variability we have. The larger the variance, the larger variability we have. And the same thing for the standard deviation. So just to go through these quickly, we have n-1. We formally call that the degrees of freedom. It comes from the theory. The formula is to derive the sample standard deviation. The sample standard deviation measures the variability about the mean, and it should only be used when the mean is chosen as the measure of center. It's always 0 or greater than 0. If you get a negative number after calculating the standard deviation or the variance, then you've done something wrong and you need to recheck. And as the observations become more variable or spread out about the mean, then the S value standard deviation will get larger. It has the same units as I talked about as the observations. So if, let's say, you have weight in kilograms, you will also have weight in kilograms for the standard deviation. In the variance, though, it will be squared kilograms, which is not really interpretable in everyday normal language. So we use the standard deviation for that reason. So like the mean, the standard deviation is not resistant. So a few outliers can change the standard deviation quite a lot. And here's the example I grabbed. I took 5 measurements from London, Ontario for 5 days in September. So I have 28, 31, 24, 25, and 32 degrees Celsius. So it was a good month, fairly good. And so calculating the mean, we add those 5 numbers up. We have n equals 5. We add them up and we get a total of 140. Divide that by 5, we get 28 degrees Celsius. Now, to calculate the variance, we denote it with an S squared. We take all the deviations. So the first observation is 28. So 28 subtract the mean 28, that's just going to go to 0. So we don't really need to calculate that one. But we still need to divide by n minus 1, which would be 4. So then we take the difference. So 31 subtract 28 here gives us 3n squared. Then 24 subtract 28 gives us -4. Now I'm leaving those brackets in because we're squaring. Because I'm adding them all, I want to put brackets around the negative values just to keep everything straight. Then 25 subtract 28 is -3, again with brackets, and we square that. And 32 subtract 28 is 4. It's positive 4, so I don't need brackets because I don't have a negative, and I just leave it as 4 squared. So 3 squared plus -4 squared plus -3 squared plus 4 squared, you're going to get 9 plus 16 plus 9 plus 16 divided by 4 is going to give you 12.5. And then that is going to be degrees Celsius squared, or squared Celsius, which is not really a common unit. So we want to get it back into degrees Celsius. So we get the standard deviation, take the square root of the variance. So the square root of 12.5 is equal to 3.54 degrees Celsius. And there you have it. We now know that there wasn't a lot of variability, 3.54. So it was just basically, plus or minus 3.54 degrees for those days in September. So it's not like it was 10 degrees difference where, you might have a location in the world where you have really extreme changes from day to day. Or let's say instead of weather, let's say I took, the price of gasoline, which can change from day to day quite extremely. So over time. So that is what the standard deviation is for. It tells us how much variability we have. And so it tells us how spread out the data is or close together. And that's the interpretation. So finally, we come to choosing the proper measure of center. So we look at the mean and the median, and we calculate them, and we go, well, do we plot the data too? We can see if we have skewness by plotting the data, or if we have symmetry. We can also compare the mean and the median, and if they're very different, then we probably have right skew or left skew. If they're close, then we probably have symmetry. So if the data is symmetric, we use the mean and standard deviation to describe its center and variability. If we have skewness, or if there's lots of outliers, then we use the median and the interquartile range to describe the distribution. So the 5-number summary, as it's stated here in the slide, is usually better than the mean and standard deviation for describing skewed distribution or a distribution with strong outliers. So use the mean and standard deviation only for reasonably symmetric distributions that are free of outliers. All right, the last couple of slides just talks about technology. We don't use the technology in this course, but I wanted to just leave this in here just to let you know that you will see some technology used in the course textbook. You can ignore it, or you can look at it as an extra resource if you want to use it. It's completely up to you.